What's going on, smart people? So today we're going to review for the first common exam for Calculus 121, also known as Calculus 2. So I have here a copy of a previous exam, so I'm going to work through the 9 problems on the exam, and well, we'll see how it goes. So over here we have a box of formulas, okay? Formulas that you're going to need for the exam. So here we have, volumes of revolution using the disk and washer method, the arc length formula, surface area formula, work, and this is Hooke's law. You're going to need Hooke's law for the problems. So let's take a look at question 1. So 1 says, sketch the region bounded by y equals ln of x, y equals 0, and x equals e. Then set up the integral to find the volume of the figure formed by rotating this area about the line y equals 3. Show a sketch of the region being revolved. Do not solve the integral. 8 points. Okay, let's see. So we have, Cartesian coordinate system over here. We have ln of x. We have the line x equals e, so this is x equals e. And we have y equals 3. Okay? Now, we're asked to revolve, the area enclosed by ln x, x equals e, and y equals 0. This area, precisely, right? And we're going to revolve it about y equals 3, okay? And, well, we can use any method to do that, okay? We just have to set up an integral. Now, let's see what we can do. Well, we want to revolve that about, y equals 3. So we have an empty space between y equals 3 and ln of x, and we have, of course, the area that we want to revolve, okay? So that sounds like, of course, the washer method for volumes of revolution. So how about we just try that? For that, we need outer radius and inner radius. So our outer radius is going to be like this. This is r of x. And the inner radius, so the radius of the inside is going to be over here. So whatever empty space you have in between the curve that you want to rotate and the axis of rotation, that's your inner radius. Let's define r of x. R of x is going to be this over here, this entire thing. Well, as you can see, if this is 0, this is 3, the distance from here to here is just 3, right? So that's 3. Little r of x, is going to be this distance. So we know that this distance over here, the value of this function has to be ln of x, right? So that's this minus this to get rid of this. So yeah, you're left with this distance. So you're left with 3 minus ln of x, So the volume of revolution using the washer method is going to be pi times the integral from a to b. Now, we're integrated in terms of x. So that means that your a in here is going to be 1, right? Since ln of x intersects the x-axis at 1. So that's going to be from 1 to e. Outer radius squared, right? So that's going to be 9 minus inner radius squared. So 3 minus ln x squared dx. And you don't have to solve for the integral, but of course, you can just simplify this a little bit, and if you do that, you're going to get something like pi integral from 1 to e of 9 minus 9, right? Minus 6 ln x plus ln x squared dx. And then you can cancel out the 9 over here, and then just distribute the negative signs. So that's going to be pi integral from 1 to e of 6 ln x minus ln x squared. So this is the answer to the first problem. I'm going to leave a link on the description of the exam, of the blank exam that I got over here, so that you can check it out. So this is question number 1. That's done. Let's see if we can move on to question 2. All right, question 2. Let's see. That was trivial, right? Okay. So now question 2. Question 2 says, suppose that a spring has a natural length of 1 foot and that a force of 10 pounds is required to hold it compressed to a length of 6 inches. How much work done is in stretching the spring from its natural length to a total length of 2 feet? Well, let's see. Let's try to make a picture of this. So we have a spring, right? And the natural length of the spring is 1 foot. And 1 foot is equal to 12 inches. And when you compress the spring 6 inches, okay, so you can imagine the spring getting smaller, right? So that's going to be the natural length. This is going to be 1 foot. And the compressed length, okay, is going to be 6 inches. So this is 6 inches and this is 6 inches because 1 foot is 12 inches, right? So we can use Hooke's law, right? F equals kx. So we can use Hooke's law to find our constant k. If we know it requires 10 pounds to compress to hold the spring at 6 inches. So that's going to be 10 pounds, right? Equals to k times 6 inches, right? All right, so we can solve for k. Usually, I would solve symbolically first instead of numerically, just plugging it in because it's better. But I mean, you can already plug it in. It's an easy linear equation, so you could just solve for that, and that's going to give you 5 thirds, right, pounds per inch. But we want that constant in terms of pound per foot, right? So how do we do that? Well, if 1 foot is 12 inches, then how many feet are 3 inches? So that's going to be 1/4 of an inch of a foot, right? So that's going to be k equals 5 pounds over 1/4 of a foot, right? So if we just bring that up, that's going to give us 20 pounds per foot. So that's going to be the constant k. And now we're asked, okay, how much work is done in stretching the spring from its natural length to a total length of 2 feet. Total length, that doesn't mean that you're stretching it 2 feet from 1 foot, right? So it's a total length of 2 feet. So it's going to be something like this, right? So this entire thing is 2 feet. But of course, the natural length has to be 1 foot. So what's the, what's the amount of, what's the distance that we're stretching this to? So this is from here to here. So we have to find delta x. So 2 minus 1 is 1. So x is equal to 1, right? So that's going to be, we're going to be integrating the work, okay, from here to here. So just imagine that this, okay, is this coordinate system, right? And this is the x-axis, this is y. So over here we have 0, and over here we have 1. So we're going to be integrating from 0 to 1. All right, so now work is going to be integral, okay, of f of x dx, right? So and then it's going from a to b, and in this case that's going to be 0 to 1. And of course, f of x is Hooke's law, kx, so that's going to be integral of kx dx from 0 to 1. And that's going to give us, okay, k is 20, right? 20, integral from 0 to 1 of x dx, and that's going to be 20 x squared over 2 from 0 to 1. And when we substitute, we're going to get 20. 20 over 2 is going to be 10 foot-pounds. So that's the work done by the spring, okay? When you stretch the string 1 more foot than its natural length. All right, let's move on to question 3. Okay, so suppose that a line segment from the origin to the general point RH is rotated about the y-axis as shown, creating a right circular cone. Find the volume of this cone in terms of R and H by using either the method of cross sections or method of cylindrical shells. So we're going to use both methods to check out the different ways in which you can do this. So first let's do the cylindrical shells. So the shell method. All right, so we know that the shell method, well, I didn't write the shell method over here, so I'm going to write it over here. So the shell method is going to be 2 pi times the integral from a to b of the radius, right? Radius times the height. And all of that dx or dy. It really depends. It really depends on, which variable you're integrating about. Hey, what's up? Okay, so we're going to do volume is equal to, but first, of course, you have to check the graph. So I'm going to show you how it looks like. Okay, so this is going to be, oof. Sorry about that. Okay, so this is going to be r, right? And the height is going to be h. All right, so let's see. And then we're going to draw a line over here. So this is point, okay, RH. And then when you revolve this area, okay, when you revolve this, you're going to get a cone, right? It's going to look like this. Good. And then we're asked to find the volume of the cone, okay? We're asked to find the volume of the cone in terms of R and H using the shell, either the shell method or, okay, or the cross-section method, which is essentially, you know, just the disk method. All right, so let's see what we can do. So in order to use the shell method, we have to find the radius. The radius, of course, is just r. So we can do volume is equal to 2 pi integral from 0 to r, right? Because we're integrated in terms of x. So that's going to be from 0 to r of the radius r times the height, okay? Times the height, which is going to be, in this case, the height is different because it's going to look something like this. This is one shell. The radius is actually, no, the radius is r, like the entire radius, right? But then the shell is going to be of height, okay, this minus that. So that's going to be h minus the function. But what's the function? We have to find the function. So in order to do that, we know this is a line, so it's in terms of y is equal to, okay? What's the slope of this line? Well, we can do h over r, so that's going to be h over r times x plus b. But of course, it crosses the origin, so that's just 0, okay? So the radius is actually going to be r, right? R, but that's just the constant, right? So it's actually x, because we're integrating a whole bunch of different shells from here to here. So the radius could be any number, so it has to be from here to here, it's got to be x, right? So the radius is actually x. So that's x times the height. The height is going to be this minus that. So this distance over here, which is h minus the function. So that's going to be h minus h over r times x dx. And then we can go ahead and integrate this. So that's going to be volume is equal to 2 pi integral from 0 to r of x h minus h over r x squared dx. And then that's going to give us 2 pi integral from, no, let's evaluate it already. So that's going to be x squared over 2 times h minus h over 3r x cubed from 0 to r. All right, so that's going to give us 2 pi r squared h over 2 minus r cubed h over 3, okay, times r. Good. Now all we have to do over here is, of course, you know, find the common denominator. So I didn't evaluate it at 0 because, of course, you have 2, okay, x's in each term, so that's just going to be 0. So let's see what we get. This is 2 pi times, okay, we multiply by 3 over here, and then times 2 over here, you get 3 minus 2 is 1, 3 times 2 is 6, so that's going to give us r squared h over 6. 2 over 6 is a third, right, because this is divided by 2 is 1, divided by 2 is 3, so that's going to give us pi r squared h over 3. That's the volume of the cone in terms of r and h. Okay, that's just the shell method, but you could also use the disk method. Okay, it's actually a little bit more straightforward if you see it that way. So let's see if we try the disk method. So that's going to be, okay, outer radius minus inner radius, right? Oh, but we only have one radius, so it's just that, right? But we have to define that in terms of, okay, in terms of y. So that's going to be x equals ry over h. So that's going to be our radius, because the cross section is going to be a circle, like that. Okay, so that's going to give us pi times the integral. And then in this case, we're integrated in terms of y, so that's going to be from 0 to the height h. So it's going to be from 0 to h of the radius squared, pi r squared. We're adding up all the disks from 0 to h. So, and that's going to be ry over h squared dy. Okay? So that's going to give us pi times the integral from 0 to h of r squared over h squared y squared dy. that gets us to pi times r squared over h squared times y cubed over 3, okay, from 0 to h. That's going to be equal to okay, pi r squared over h squared times h cubed over 3. And well, h cubed over h squared, that's going to be h. So the amount, the volume is going to be pi r squared h over 3. So we get the same answer for this method. But this is actually a little bit more straightforward, so I'll go with this. So for question 4, we're asked to find the volume of the figure formed by rotating the area bound between y equals x squared and the y equals 2x, about the y-axis. And we're asked to do it using any method. So we have several options here, to solve this problem. But first, let's make a little sketch to see how this is going to look like. So if we're going to revolve it about y equals x, it should look like something, something like this, right? And then it's going to be revolved, so it's going to form circles, right? Something like that. And then this is going to be the solid area. Right in the middle, we're going to have an empty space, right? So this is going to be the volume. Now we have several options. We have volumes of revolution, using the disk method, or shell method, or there is another way to do it, which is a shortcut. But I'm going to show you that at the end. Now, first of all, let's try the disk method. So we're going to have to revolve this about y. So the outer radius is going to be this over here. This is the outer radius, and the inner radius is this. Now the outer radius in terms of y, we're going to do it in terms of y, so we have to define each of these functions in terms of y. So x squared in terms of y, that's going to be x equals the square root of x, right? Sorry, x equals the square root of y. Yeah. And this in terms of y is going to be x equals y over 2. So now let's build up our integral. So the volume has to be pi times the integral from here to here, right? So whatever they intersect, because we're integrated in terms of y, we have to find the y value, at this point of intersection. To find the points of intersection, well, we could just set up these functions equal to each other. So 2x equals x squared, and we have x minus 2 is equal to 0. So that means the intersections are at 0 and 2. Now when we put 2 into x squared, we get 4. So that's going to be the value of the function. So we're integrating from 0 to 4.
Do not lose my laptop.
Joe Mama.
So we're going to integrate from 0 to 4. And it's going to be r. So it's going to be the square root of x squared, right? So the square root of x squared, that's going to be the outer radius, minus the inner radius, which is going to be x over y over 2 squared, dy. So the volume is going to be equal to pi times the integral from 0 to 4 of y, right? Y square root of y squared is y, minus y to the minus y squared, divided by 4. 2 squared is 4 dy. Now the volume is going to be equal to pi times y squared over 2 minus y cubed over 4 times 3 is 12 from 0 to 4. Then let's evaluate that. So that's going to give us 4 times 4 is 16, divided by 2 is 8. And 4 times 4 is 64, right? But if we take one factor of 4 and then we simplify this, we're going to get 4 divided by 4 is 1, right? So that's going to be minus 4 times 16, right? 4 times 4 is 16 divided by 12. If we simplify this, this is going to give us 1. This is going to give us 3. Then we find the common denominator. This is going to be 8 times 3 is 24. 24 minus 16 is 8. So we get 8 pi over 3. These chalks keep breaking. So this is going to be the answer for this using the the washer method. This is the washer method because we have an empty space in between. Okay. Now let's try to use the shell method next. Okay. We have to find, okay, of course, what the radius is and what the height is. So let's see what we can do. Okay, to use the shell method, okay, we need the radius, right? The radius has to be the change, okay, in what variable? We have to find the radius in change in terms of the change of x, right? So the radius has to go from the axis of rotation, which is y, to any point on the function, right? On this side of the function. So this is, for example, if we take a shell here, this over here will be the radius for that shell, for that specific shell, and the height will go all the way up to the value of the function that we're integrating to, right? And then it's going to look something like this, right? So this is going to be one shell. Okay, and then the radius, we said it was going to be, okay, a change in x. So it's just going to be x, right? Any distance x from the center of rotation to the curve. So radius is x. Now the height is the difference between the two curves, right? So in this case, we're finding the difference from here to here, right? Oh, so yeah, this over here. Yeah, no, I'm sorry about that. Let me actually just redraw that so you can see it easily, because it's just a whole bunch of lines in there. So okay, so we have y equals 2x, which is x equals y over 2, and we have y equals x squared, which is just x equals square root of x, square root of y, right? We did that for the last problem, and now so it's going to look something like this. So we have x squared like that, and then y equals 2x. Now the radius, like we said, is a change in x, right? So this is the radius over here. Let's say we take a typical shell over here. So let's say it's going to be something like this, right? So this is the radius. That's going to be x, a distance x from the center of rotation, which is y, okay, the y-axis. Now the height is going to be the difference between the top curve and the bottom curve. So it's going to be this over here. It's not going to be, up to the function. So I was wrong about that, but it's going to be like that. So we kind of, draw the resulting, okay, rotation. It's going to look something like that, and then we're going to have something like that. Okay. Now the shell is going to look like this. It's going to intersect this. Going to go down like that. And then we're just going to add up all the shells, okay, from this value of x to the value of x where these two curves intersect, and we found that it was 2, right? Which means that the value of y has to be 4. Okay. And now we're integrated in terms of x because the shells are perpendicular to the x-axis, okay? So let's see what we can do. We know the formula is 2 pi integral from a to b over the radius times the height times dx. So the volume is equal to 2 pi times the integral, okay, in terms of x is from 0 to 2. So it's from 0 to 2, okay? The radius we said was x times the height is a change, okay, in the functions. So this is this minus that in terms of x. So that's going to be 2x. The top curve is a line, so 2x minus x squared dx. And now we can integrate, we can distribute this. So that's going to get us 2 pi integral from 0 to 2 of 2x squared minus x cubed dx. Okay? And we can integrate that, so that's going to give us 2 pi times 2/3 x cubed minus x to the 4th over 4. And then, okay, we're integrating from 0 to 2. So that's going to get us 2 pi times, okay, 2 to the 3rd is going to be 8, so that's going to be 2 times 8 is 16, right? So that's 16 over 2 over 3. And 2 to the 4th is, I'm sorry, that's right, because we multiply by 2, so 2 to the 4th is 16, so that's going to be 16 over 4 is 4, right? So that's minus 4. And we don't have to plug in 0 because we already know that's going to be 0. So we find the common denominator here. 4 times 3 is 12. 16 minus 12 is 4. So it's 4/3, right? So 4/3 times 2 is 8/3. So that's going to give us 8 pi over 3. So that works, okay? The shell method is actually a little bit more straightforward. The only thing is the setup, okay? You have to be careful with the setup. the radius is always with respect to, okay, the axis of rotation, so you're calculating, okay, the distance, a change in this distance, okay, from the axis of rotation to the curve. So that's going to be x in this case. Now the height is the difference, okay, between the two curves, because we're revolving this area, right? So you got to remember that. And then we're going to add up all the shells. Good. Now, but there is another way to do this, and it's actually even more straightforward. It's just that maybe you skip a little bit of steps, and I don't know if it's going to be allowed on the test. I mean, the question says that you can use any method to find the volume, okay, revolved, okay, when you revolve this area. And one way you could think of this is, well, when you look at this a little bit deeper, right, you could see that this line makes a triangle, okay, with the vertical, with the y-axis. And if you revolve the triangle, okay, about the y-axis, you're going to get a cone, right? And remember, we derived the formula for the volume of a cone in the last problem. So maybe we could use that formula to find this volume of the cone. So let's see what we could do with that. So the volume of the cone, okay, is equal to pi r squared h over 3, right? And we know the radius of the cone, right? So it's this distance from here to here, so which is 2. So we can plug that in there. So pi over 3 times 2 squared. And then the height is from here to here, right? The height of the cone goes from here to here. That's going to be 4. So that's going to be times 4. And that's going to get us, okay, 2 times 2 is 4. 4 times 4 is 16. 16 pi over 3. Okay? But now, we're not trying to find the volume of the cone. We're trying to find the volume of this area that when it is revolved, right? So essentially, one thing you could do is, well, use the disk method to find the volume, okay, revolved when you revolve this entire area. So you're only going to be using one function, this function over here, y equals x squared. And you're going to find the volume. So if we do that, we're going to get, okay, pi times the integral. Okay, this is going to be in terms of y, right? Because the radius is perpendicular to the y-axis. And that's going to be x equals the square root of y. So that's going to be from 0 to 4, right, of the square root of y squared, pi r squared, right, dy. Now this cancels out. Oh my goodness. Okay, sorry about that. That cancels out. And that's going to give us pi integral from 0 to 4 of y dy. And that's pretty easy, right? So that's going to give us pi y squared over 2 from 0 to 4. And that's basically 4 times 4 is 16 over 2 is 8. So that's 8 pi. Now, how do we find the volume of this only? Because we just found the volume of the entire thing. Well, you guessed it. We just subtract the volume, okay, of the entire thing minus the volume of the cone. So let's see what happens if we do volume of the cone, right, minus the volume total. That's equal to 16, okay, oh, actually it's the other way around. The volume of, the total volume minus the volume of the cone, yeah. So it's the total volume, okay, volume total, minus the volume of the cone. And the total volume is 8 pi, volume of the cone, 16 pi over 3. Found the common denominator, and you're going to get 8 pi, okay, over 3. And it's exactly the same answer. It's actually more straightforward, right? Well, that's just a trick, good trick to know. All right, so let's move on to the next question. Now, the next question is, find the volume of the figure formed by rotating the area bound by the x-axis and the cubic, y equals x squared minus x cubed, about the y-axis. All right, so let me erase this. Okay, so now we have something like this. Okay, for question 5, we have something like this, right? This is y, this is x, and we have, we're going to revolve the area by the x-axis, right? And it's going to be a cubic function, and that's going to be y is equal to x squared minus x cubed. All right. So it's going to look something like this. Okay, so this is the cubic function over here. Okay, but we're only looking at whatever is enclosed between the x-axis and the cubic, right? And we're going to revolve that about the y-axis, if I'm not wrong. Yeah, we're going to revolve it about the y-axis. All right. So let's see what we can do. All right, so let's see how is this going to look like once we revolve it. Once we revolve all this area, okay, when we rotate this area, it's going to look like this, right? And then we can make something like that, right? That's going to be, okay, a good approximate. Then forget about this line. All right, now, there is only one method you could use, which is very straightforward, right? If you think about it, you are not going to be able to use, okay, the washer method, because that's going to be very hard to, come to. You're going to have to use the cubic formula, and that's annoying. Okay, that's very long. So let's use the shell method. Now, for the shell method, we need the radius, we need the height. The radius over here, about, the y-axis is just x. So let's assume this is one shell. Okay, so this is one shell. The radius is x. The height is just the function itself. So it's x squared minus x cubed. So let's find the volume of the solid. So that's going to be 2 pi times the integral from a to b. Now in this case it's in terms of x, right? So it's from here to here. Where does it intersect? Well, if you factor that, you're going to get x squared and then 1 minus x, right? So it intersects at 1, right? So this is 1 over here. So it's from 0 to 1. Okay? Of the radius. The radius we said it was x, and the height is the function itself, so it's x squared minus x cubed and dx. Now we can integrate this easily. So this is going to be 2 pi times integral from 0 to 1 of x cubed minus x squared dx, and that's going to get us 2 pi times x to the 4th over 4 minus x to the 5th over 5 from 0 to 1. Okay, now we just substitute, so the volume is equal to 2 pi times 1/4 minus 1/5. Use common denominator, right? Find the common denominator. That's going to get to 2 pi times, this is going to be 1 over 20. And when you simplify, you're going to get pi over 10. Pi over 10 is the volume of the solid generated by the cubic, okay, by revolving this cubic, this area enclosed by the cubic, and y equals x, the x-axis. Okay, so now let's move to question 6. All right, that was pretty easy, right? So just remember that when you want to find the radius using the shell method, the radius is always with respect to the axis of rotation. Okay, so it's always relative to that axis of rotation. Now, for question 6, right? Question 6, we have evaluate the integral of cosine of the square root of 3x over the square root of x dx. Okay, so evaluate, okay, integral of cosine the square root of 3x over the square root of x dx. All right. Well, what can we observe in this integral? Well, one thing you see over here is that you have two radicals, okay, one on the top and one at the bottom. This one is inside the cosine function. So let's see what we could do. Maybe we could try a substitution, right? How about we just let u equal to whatever is inside our cosine? It makes our lives a lot easier, right? So let u equal to the square root of 3x, right? Which means that du is going to be 3, right? The derivative of the inside, we use the chain rule, is going to be 3. The derivative of 3x is 3 divided by 2 times the square root of 3x. All right, dx. That's going to be du. Now, as you can see, you have a dx over the square root of x. So how about we find dx over the square root of x, given this over here? So we can multiply by 2, divide by 3. So we have 2 over 3 du, and then we have dx over the square root of 3x. It's close, right? dx over the square root of x, dx over the square root of 3x. What do we have to do? Well, how about we just take the square root of 3 out, and then we just multiply it on the other side. So let's multiply by the square root of 3 on both sides. And that's going to be equal to dx over the square root of x. And we have that over here. Okay, so let's substitute. Okay, integral of cosine of u du, right, times 2 times the root 3 over 3. Integral of cosine of u du is what? You know, it's going to be sine, right? So it's going to be 2 radical 3 over 3 sine of u plus c. Don't forget your c, right? That's very important. You're going to get a lot of points off if you don't put c, your arbitrary constant. Now let's substitute back into u. So that's going to be 2 root 3 over 3 sine of the square root of 3, right? X plus c. That's going to be the integral, okay? Not very hard to do. Just try to look for, okay? These substitutions, they're very useful. Now let's move on to question 7. So find the arc length of the curve x equals 1/6 y cubed plus 1 over 2y between 1 and 2. Okay, between y equals 1 and y equals 2. All right, so let's see what we can do. For question 7. All right, so for question 7, we have x equals, okay, so x equals to y cubed over 6, and then plus 1 over 2y. And then we're going to integrate it from 1 and 2. So, okay, so 1 is less than or equal to y, and that's less than or equal to 2. All right. Now, how is this going to look like? Well, that's a good question. Let's see if we could try to graph this, right? So, what happens when, okay, this is going to look like, let's see. If we find the common denominator, well, that's going to be y to the 4th, right? Y to the 4th times 2 plus, okay, plus 3, right? And then divided by 6y. All right, this is a rational function, right? So let's see what this is going to look like. All right, so what if we try just plugging in some values of x over here? So what happens when x equals 0? Oh, look at that. When x equals 0, I'm sorry, when y equals 0. When y equals 0 is undefined, right? So we know for sure that there's going to be an asymptote at y equals 0. Okay, so at y equals 0 there has to be an asymptote. Now, let's see where this asymptote is being approached from. So now let's plug in, for example, y equals 1, right? So we get 2 plus 3 divided by 6. 2 plus 3 is 5, so it's 5, 6. So it should be somewhere around here. So this is 1, this is 5/6, and this is 1. Did we try plugging in x equals 0 to find the y-intercept? Well, let's see what we get. When x equals 0, okay, that's going to give us 2y to the 4th plus 3 equals 0. And as you can see, you're going to have imaginary solution. Because when you take the 4th root of that, you know, you're going to get an imaginary number. All right, so that means it doesn't touch the y-axis either. So my best guess, all right, my best guess is that it's going to look like this. Okay, so we have two asymptotes. We have, okay, the y-axis and the x-axis. And we want to find the arc length from 1 to 2, from y equals 1 to y equals 2. Okay, the arc length. So this is going to be that arc length. And we're trying to find that arc length, okay? So now we know the formula for the arc length. It is going to be the integral from a to b, okay, of the square root of 1 plus the derivative squared. So let's try to find what. So we know our function. We know it's x, right? Now let's find the x. So in this case, we can rewrite the formula in terms of x. So integral from a to b of the square root of 1 plus dx over dy squared dy, right? Because we're integrating in terms of y now. All right, so let's see what we can do now. So we know x, but we don't know dx, so we have to find dx. Now dx is equal to the derivative of this, right? So that's going to be 3, okay, 3y squared. 3 over 6 is a half, right? So that's going to be y squared over 2, okay? And then this is going to be minus 1 over 2 y squared. All right? This is going to be the derivative. Now, what happens when we square this? When we square dx over dy. All right? So this is going to get us y to the 4th over 4 minus 2 times a times b. Now, 2 times 1/2 is just 1. So we have y squared times negative 1 over 2 y squared. So y squared over y squared is 1. So we get 1/2. Nice. And then plus this squared, 1 over 2 y squared squared, that's going to give us 1 over 4 y to the 4th. Okay, this is going to be the derivative squared. Now we can plug that in the formula for the arc length. That's going to give us integral from a to b of the square root of 1 plus y to the 4th, right, over 4 minus a half plus 1 over 4y to the 4th. Now look at this. Pay close attention to what's going to happen. 1 minus 1/2 is what? 1/2, right? Oh, this is the 1. So that's going to be 1/2, right? If we subtract 1/2 out of 1, that's going to get us 1/2. Very good. Now compare this over here. Compare this trinomial. Okay, compare this trinomial. Well, this is not really a trinomial. It's just a function, right? We found out that it's going to look like this. Compare that to this, right? What's the only difference? It's this sign, right? This sign is the only difference. This is a perfect square. It's this squared, right? This binomial squared. And the only difference is the sign. So what if we just switch the sign over here and then we square it? This is a perfect square, by the way. Okay, so let's see what we get. So if we try to square that, so y squared over 2 plus 1 over 2y squared, if we try to square that, you're going to see that you're going to get exactly the same as this. Y squared over 2 squared is going to be y to the 4th over 4. Plus 2 times ab, so plus 2 times y squared over 2, that's going to be y squared, times 1 over 2y squared. Y squared over y squared is 1, and you're left with a half, positive 1/2. Now, when you square the last term, you're going to get this. So that works out perfectly. And you can get rid of the radical sign. So L is equal to integral from, and then A is going to be what? 1, right? So that should be defined already. So that's 1. And B is going to be 2. So integral from 1 to 2 of the square root of this squared, right? So that's going to be y squared over 2 plus 1 over 2y squared. And the radical cancels out with the squared dy. And then we can integrate that. Okay, so let me just get some space over here. So we're going to have, okay, integral from 1 to 2 of y squared over 2 plus 1 over 2y squared dy. And that's essentially, okay, y cubed over 6 minus 1 over 2y from 1 to 2. Then let's substitute that in. So that's going to give us 2 to the 3rd is 8. So that's going to be 8 over 6. Okay. 1 over 2 times 2 is 4, 1/4. So it's going to be minus 1/4. And then minus, we have to subtract the lower limit. That's going to give us 1/6 minus 1/2, right? All right, now let's see what we can do here. 8/6 minus 1/6 is 7/6. Negative 1/4 plus 1/2 is 1/4. Use common denominator. Okay, this is 2 times 2. This is 3 times 2. So multiply this by 2. Multiply this by 3, right? And then multiply this by 3, 2. You're gonna get 14. Okay, over everything over 12, and then this is going to be 3 plus 3, and the answer should be 17 over 12. Okay, 17 over 12 is going to be the answer. All right, very good problem, very good problem. Now let's move on to the next problem. Now problem number 8. It's a total of 9 problems, so we're getting close to the end. Okay, so problem number 8. Find the surface area of the paraboloid formed when the curve x equals y squared from 0 to radical 2 is revolved around the y-axis. I mean the x-axis. Okay, so we have something like this. X equals y squared looks like this. Okay? And then we want to revolve that. Okay, we want to revolve that. The limits are going to be from 0 to radical 2. So 0 is less than or equal to y, less than or equal to radical 2. So the limits are going to be from here to here, and this is radical 2. All right, so it's going to be something like that, right over here. Good. All right. And we're going to revolve this, of course, about the x-axis, something like that. Okay, that's x, that's y. And then we're going to get a paraboloid. So that's what you get when you revolve a parabola, okay? So that's going to be something like this, right? That's going to be the paraboloid. All right, close. Not best. I'm not a good drawer. All right, not a good artist. But let's see what we get. All right. So, well, I mean, technically, what's the easiest method you could use here? You know, just this method. So let's try this method. The radius is this. So the volume should be equal to, okay, pi times the integral from here to here. Now, what's this over here? The x value. If we know that this is radical 2, and this function is x equals to the square root of y. If y equals radical 2, okay, that's going to be what? That's going to be 2, right? Yeah, because, no, that's going to be radical 2. So y is equal to x squared. If y is radical 2, that's going to be 2. Yeah, that's going to be 2, right over here. So we're integrating from 0 to 2, okay, of x squared dx. And that's going to get us pi x cubed over 3 from 0 to 2, which is equal to 8 pi over 3. And, well, there you go. That's the answer. Pretty straightforward, right? All right, so for question number 8, we're going to find the surface area of the paraboloid formed when the curve y equals the square root of x in between 0 and radical 2 is revolved around the x-axis, okay? So it's essentially something like this. So we have y, x, and x equals, okay, the radical y, right? So we're going to have something like this, right? Oh, I'm sorry, no, that's not how it is. It's supposed to be So for question number 8, we're going to find the surface area of the paraboloid formed when the curve x equals y squared, okay? So x equals y squared is revolved between 0, okay, and radical 2, when it's revolved about the x-axis. So about x. About the x-axis. All right. Now we're going to have something like this. So x equals y squared is going to be like that, only for the top part, right, for the first quadrant. And we're integrating from 0 to radical 2 for the y value. So let's say that this is radical 2, which means that our x value, okay, has to be 2. Right, because when we plug radical 2 into y squared, that's going to give you 2. So we're going to revolve this about the x-axis, and we're going to get something called a paraboloid. So it's going to look like this. Okay, that's going to be the paraboloid. All right, and we're going to find what? Not the volume of revolution, but the surface area. Okay, we're going to find that area of the surface. Now we know that the surface area is defined as 2 pi times the integral from a to b of the function multiplied by the arc length, okay? Multiplied by the square root of 1 plus the derivative of the function squared dx. So surface area is equal to, okay, in this case, what's our function? Well, our function, if we're doing this in terms of x, right, that should be, okay, y equals the square root of x, right? So y is equal to square root of x. So we're doing this in terms of x, right? We're revolving this about the x-axis. And over here, this function is, okay, perpendicular to, this radius over here is perpendicular to the x-axis. So we're doing that in terms of the x-axis, in terms of x. So that's going to be 2 pi times the integral from here to here, so from 0 to 2, okay, of the function itself. So that's going to be the square root of x times the arc length, so the square root of 1 plus dy squared. Now, if we have y is equal to the square root of x, dy should be 1 over 2 square root of x, okay? So dy over dx is that. So we could put it in, so 1 over 2 radical x squared, okay, dx. Now let's see what we get. That's going to be 2 pi integral from 0 to 2 radical x times radical 1 plus 1 over 2x, 1 over 4x, because it's 2 squared, right? And radical x squared is x. All right, dx. Now look at this. We're multiplying two radicals together, and you know, if they have the same power, we can bring this inside and see what cancels out, right? So let's see what happens. So we have 2 pi integral from 0 to 2 of the square root of x plus, and then what's x over x? That's 1, right? So we get 1/4 dx. And of course, this is pretty easy to integrate, right? If you use a u substitution, you're going to have du is equal to dx. So that's very nice. So the surface area is going to be equal to 2 pi times x plus 1/4 to the power of 3/2, right? Times 2/3. That's going to be from 0 to 2. All right, and then let's substitute and see what happens. So that's going to be 2 pi, 2 plus 1/4. That's going to give you what? 4 times 2 is 8. 8 plus 1, 9. So 9/4. Okay, 9/4 minus. Oh, we're integrating from 0 to, so that's going to be 0. So we're going to be left with 1/4. And all of this has to be to the power of 3/2, right? So that's going to be to the power of 3/2. Good. Now, this means that it's being square rooted, right? So what's the square root of 9? That's 3. What's the square root of 4? That's 2. So we have 2 pi times 3 over 2 cubed, right? We're left with the cube minus what's the square root of 1 is 1, what's the square root of 4? That's 2, so that's going to be 1 over 2 cubed. And then we finally have 2 pi times 3 times 3 is 9, right? 9 times 3 is 27. So that's going to be 27 over 2 to the 3 is 8 minus 1 over 8. 27 eighths minus an eighth is 26 eighths. So that's going to be 26 eighths multiplied by 2 pi. Over here, we get, okay, we can simplify this a little bit, right? And we're going to be left with what? We divide this by 2 over here, that's going to be 13, right? 13 times 2 is 26, and this is 2. So this is 13 pi over 2. All right, so that's going to be the surface area of the paraboloid. All right. So let's move on to the next problem. The last problem, very last problem of this practice exam for Calculus 2. All right, this is interesting. Let's see what we're going to get. Where's the razor? Oh, here it is. Question 9, last question. Now for question 9 we have, okay, suppose that a cylindrical tank is buried upright underground. Alright, so we're going to make a cylindrical tank that's buried underground. So that you have a cylindrical tank like that. Okay, good. Now it's buried underground, so let's say that this is ground level. Alright. And then, okay, the tank has a height of 6 meters. Okay, so the tank itself has a height of 6 meters. So this over here is 6 meters. And the radius is 2 meters. So the radius over here is 2 meters. Now, suppose the top of the tank is exactly 3 meters below the Earth's surface. So this over here, the distance from here to here is 3 meters. Okay, this is ground level. Good. Now, if the tank is half filled with water, weighing approximately 10,000 newtons per meter cubed. So it's half filled with water. So this is half of it. Suppose it's half. And then its weight is 10,000, okay, newtons per meter cubed. Now, let's see what we have. Find the work needed, okay, to pump all the water in this tank to the ground surface. So somehow, I don't know how, maybe with some sort of, mechanism, or maybe by hand. You never know. I mean, it's not like it's very big, right? It's not a very big tank. Maybe with some hose, right? Some vacuum. They're going to get this water. They have whatever water is in the tank. We know it's half filled. Okay. We're going to get this water above the Earth's surface. So from here to here. Okay, so that means the lower part, okay, of the water, okay, the water level, is going to be on top, okay, at the surface, at ground level. Now we were told that the tank was half filled, and that the height of the tank is 6 meters. If it is half filled, what's half of 6 meters? That's 3 meters. So this distance, it's 3 meters. Good. Now, let's imagine that you have a coordinate system, okay? Let's make a coordinate system to make things simpler. This is y and this is x. This is y over here. This is y equals 0, okay? This is y equals 0. Over here, we have what? Y equals 3, right? And over here, we have y equals 6, because the height of the cylindrical tank is 6 meters. So this over here is 6, the value of y, right? Oh, right over here. And we're left with 3 meters to add, right? So what's 6 plus 3? That's 9. So that's y equals 9. Good. Now remember, these are y values for the coordinate system. Good. Now we're trying to find the work done, needed, okay? The work needed to get this water out of this tank into the on top of the Earth's surface. So we have to follow a few steps. First of all, we need to find an expression for the volume of the water. All right? So for the volume of the water, we're going to have to do volumes of revolution, right? We're going to imagine that we have an infinitesimal disk, okay, over here. And we're going to add up all those disks from here to here, from 0 to 3. Very important to keep in mind. We're only adding disks from 0 to 3. Okay, so we're going to have pi times the radius squared, so pi r squared, and the radius is what? We were told that it was 2 meters. 2 squared. Okay, pi r squared times, okay, the change, okay, the change in y. So that's going to be dy. All right. That's step number 1. Now, step number 2, we need to find the force, because remember, what's the definition for work? Work is equal to the integral of force times distance for f of x dx. We found force, we found the distance. We haven't found the distance. We need to find the force. We only found the volume, and we know volume has units meters cubed, right? Cube meters. That's the units for the volume. Now we have a weight defined as 10,000 newtons per meter cube. If we multiply the weight by the volume, okay, we're going to get its force, or the weight, essentially, right? Because this is just the density. They say it weighs 10,000 newtons per meter cube, but it's just the density, okay? We're going to multiply the density by the volume to get the force, or the actual weight, right? So we're going to have, for the force, we're going to have 10,000 newtons per meter cubed multiplied by the volume, which is 2 times 2 is 4, so that's going to be 4 pi dy, meters cubed. The meters cubed cancel out, and we're left with this expression for force. 10,000 times 4 pi dy, which simplifies to 40,000 pi dy. All right, that's the force. We found the force. Now we need to find the x, the distance. We need to find the distance, right? Well, in this case, it's dy is okay, the infinitesimal thickness of the disks. So it's not dx, it's dy. But we need to find, okay, the distance from here to whatever we're doing work. So like we're pushing the water from this, okay, from this point to all the way to the top, right? So that's going to be from here to, from y equals 0 to y equals 9, right? Remember? So to find the distance at any point, suppose that the water level is over here, okay, at some arbitrary value of y. The distance that's left for us to push is this. And how can we define that distance? If, let's say, the water level is at this point of y, right? So the distance has to be this minus that. So the difference is going to be 9 minus y. That's the distance, okay? Distance is 9 minus y. Now, we have to finally, okay, plug in all these values that we found into the definition of work. So work is equal to the integral from a to b. Now, this is very important to pay attention to. The lower and upper limits depend on the volume. They depend on wherever the volume is being integrated, right? The volume is getting integrated from 0 to 3, not from 0 to 9. We're not integrating the volume from 0 to 9, right? So we're going to be integrating from 0 to 3. Now, we're going to multiply that by the force, right? F of y in this case, which is 40,000 pi, and the y goes after. I'd like to put it at the end. And that's multiplied by the distance. Distance is 9 minus y. Good. Now we have an expression, and we can find the work done. So let's see what we can do. We can take these constants out of the integral, right? So let's see what we get. Work is equal to 40,000 pi, okay, integral from 0 to 3 of 9 minus y dy. Now this is a very easy integral to do. So let's see what we get. That's going to be 40,000 pi times 9y, right, minus y squared over 2. Very good. Now, the limits are from 0 to 3, and we can already plug that in there, so we're going to get work is equal to 40,000 pi times 9 to the 3 times 9 is 27, right? And 3 squared is 9, so that's 9 over 2. We found the common denominator. We don't have to substitute by 0. That's going to give us 0. Okay, so right over here we have to find the common denominator. So that's going to be 27 times 2 is 54. 54 minus 9 is 45. Okay, so we have 40,000. Okay, 40,000 pi times 45 over 2. And we can simplify this over here. 40,000 divided by 2 is 20,000. And then we have 20,000 pi times 45. So let's see, we multiply 20 by 45. And that's going to give us what? 900, right? That's going to give us 900. And then we just have to add up all the remaining zeros. So, but this is 3 zeros, so we could define this as, okay, the work done is going to be equal to 900 pi, okay, kilo for 1,000, because we're multiplying by 1,000, right? Kilo. And then what are the units for work? Okay, in the metric system is joules, so kilojoules. So the work done is 900 pi, okay, 900 times pi kilojoules. All right. So I think that's it for now. Thanks for watching, and good luck on the exams. I'm gonna keep posting more videos on any sort of interesting integrals or exercises in calculus, in hopes to help you out. Okay, so give it a like, subscribe, share it with your friends, and make sure you study. Okay, study on time. Don't procrastinate. All right. Thank you. I'll see you next time.